Welcome to this advanced higher video for the electromagnetism unit. This is on Coulombs Law, the electrostatics part of the course looking at the forces between particular charges. So this lesson is all about looking at Coulomb's law and being able to use the appropriate relationship to solve problems looking at electrostatic forces. For a single charge or, well, two charges or a complete system of charges. So let's look at the things that we already know about charges. Well, we know charge is a physical property like mass. We know that charges experience a force when placed in electric fields, and that there are two types of charge, positive and negative charges, and that like charges repel and opposite charges attract. We also know that this fundamental unit of charge, the charge on an electron, 1.6 times 10 to the minus 19 coulombs, and we get whole multiples of those in any particular quantity of charge, apart from when we're talking about the charges on sort of individual quarks, but quarks don't live by themselves, so therefore we always end up with a multiple of the fundamental charge. So here's Charles Coulomb, and he discovered a law that described the forces between charges, and this is very similar to Newton's law of gravitation between two masses. Here we have the electric field patterns around two charges. So if we consider two charges, charge Q1, charge Q2, and separated by a distance r, just like the gravitational rules, we use r rather than d for distance. And Coulomb found that the force depended upon the distance that the charges went away, but it was inverse square relationship between the two, in the same way that there's an inverse square relationship for gravitational forces. It also depended on the product of the magnitude of the two charges. So he ended up with a relationship like this one. Okay, where k is our constant. Now the Newton had already been defined in terms of the force needed to accelerate 1 kilogram of mass at 1 meter squared from Newton's second law, F equals ma. So it turns out that the force between 1 coulomb of charge 1 meter away from another coulomb of charge is not 1 Newton, so the constant is put in between the two, and just like big G for Newton's law of gravitation. So the constant here is approximately 9 times 10 to the 9 between the two. This is usually expressed in a particular form, 1 over 4 pi, and the character there you can see is the Greek letter epsilon, and it's called epsilon naught, which is also called the permittivity of free space, and that's sometimes called the electric constant in some documents as well. And that has a particular value, epsilon naught, which is on your data sheet, 8.85 times 10 to the minus 12. So one of the differences between Coulomb's law and Newton's law of gravitation is that for gravitational forces, they're always attracting, whereas because charges can have like or unlike charges, we can have forces that are attracting or forces that are repelling between the two. Okay, so instead of writing it with our constant, we can put in our constant 1 over 4 pi epsilon naught. So sometimes you see it written like that, or you can combine the two as you see on your relationship sheet. It is good practice in advanced higher physics to substitute into the numbers. You don't need to substitute in pi in your calculations. You can leave it pi for the substitution step, but you should put in epsilon naught. It does happen to be that 1 over 4 pi epsilon naught is 9 times 10 to the 9, so you will see some shortcuts using this method, but you are best to substitute in the individual constants too. And as I said before, it's 8.85 times 10 to the minus 12 farads per meter. So let's have a look at an example of working out the forces. So here's our problem. We've got two forces, a 3 nanocoulomb charge on the left and a -5 nanocoulomb charge on the right, 7 centimeters apart from each other. And we need to work out the force between the two. So we can look at our variables, remembering that distance should be in meters and taking into account any prefixes that we need to do, and then we can substitute into our equation. Okay, notice here we've put in the signs of the charges and we've got a negative charge on the force, which is meaning that the force is going to be attractive between the two. Depends on which point of view we're looking at. Are we looking at the 3 newtons Coulomb force, in which case that will move towards the 5 one to the right, or are we looking at the -5 Newton Coulomb force, in which case the force on that is moving towards the left. So if we're going to put a direction on it, we need to have a bit more information in the question. Okay, but the negative charge does show that it's got an opposite sign, and so the things are going to be attracted. Okay, let's have a look at another one now. We've got 3 forces. This time they're not all in a straight line. One is down at the bottom and the other 2 are at the top. So if we consider the forces on B, then B, because of charge C, will be repelled from charge C because they've both got negative charge, and B will be attracted downwards by A. So the diagram on the right is kind of indicating the direction of the forces. This is sometimes quite a good approach to take because it can make sure that you get the directions and everything correct. Because force obviously is a vector, so we need to solve this in a vector type approach. So here's our diagram again. We can work out the force between A and B and the force between B and C by substituting in the numbers. Okay, we were then asked to work out what the overall force was, so we need to take a vector approach, drawing a vector diagram. So we've got the force that we just worked out for A and B, and we've got the force for B and C there. I've just put the magnitudes of the forces on this diagram because I've already considered the directions in terms of the arrows to make sure that they're drawn top to tail. And then we're going to work out the resultant, and because these are at right angles to each other, we can do it in the normal way using our Pythagoras relationship to get our value. Okay, because force is a vector, it should also have a direction, so we're going to use some trigonometry to work out the direction, because we've got the opposite and the adjacent sides of the triangle, so we can work out that it's an angle of 80 degrees from the vertical. So we might need to make some reference to where we're measuring that from, or draw it on our diagram. Obviously, unlike some other things, we're not really talking about north, south, east to west in most cases. We're talking from a particular datum point. Okay, so here's another problem that you could try yourself. See if you can use your pen and paper to find out the force that is acting upon B due to charges C and A. So if you pause the video whilst you work out the problem, and then you can look at this answer. Okay, so here's the answer. We have 2 particular forces between the two. The one force is much greater, the force between A and B, downwards, than the force between B and C, so that makes the angle from the vertical very, very small in this particular case. Okay, so you should now be able to carry out calculations to solve problems on electrical forces or a system of forces, and should now complete the questions to give you this practice.